Hello everyone, my name is Yubo Zhang. I'm currently a second-year PhD student in UIC, focusing on NLP, especially in the safety and fairness issues of large language model. Today, I will present several papers about data attribution generally related to NLP scenarios. I'm also new to this field, so please feel free to correct me and contact me if I get anything wrong. I really appreciate it. Here is the outline of my presentation. We will start with the 2022 paper that was the first one to apply influence functions in NLP, allowing us to propose the black box of model predictions and uncover hidden data artifacts. And then building on this one, the 2021 paper combined the feature and instance level attributions, enhancing our ability to detect the patterns in influential training samples by integrating word-level feature analysis on the influential training samples. These first two papers mainly aim to use empirical influence function to identify the artifacts in the dataset. Next, a more recent paper in this year focused more on how these artifacts influence the model's behavior after fine-tuning, and which offer a more nuanced understanding of the fine-tuning process with several key properties learned from the fine-tuning. And the last one, 2022 paper, pointed out a very specific challenge known as the cancellation effect by using the last layer of large model for the influence analysis. We study these foundation papers because they still provide critical insights into understand and interpreting models' behaviors, which remains essential even as we advance to larger and more complex large language models today. Let's start with the first paper that introduced the influence function to understand data artifacts for NLP models. Firstly, we should know what is an artifact in the context of NLP or language. In NLP, an artifact is a pattern in the data that a model learns, but it doesn't actually reflect the true nature of the language. Instead, it's often a quirk of the training data or process. These artifacts can lead to models making predictions based on these misleading patterns rather than understanding the language itself. And this can result in poor performance when the model is applied to a new and real-world data, as it overfits to these artifacts rather than generalizing from the true language features such as the semantic meaning. For example, for this sentiment analysis model, which is trained on a dataset where the word great is frequently appears in the positive reviews and the word awful frequently appears in the negative reviews. However, the training dataset is very imbalanced, with very few examples of the great word used sarcastically in the negative context, such as the service was greatly terrible. As a result, the model might develop an artifact where it always associates the word great with positive sentiment, leading to incorrect predictions while sarcasm is involved. Therefore, this motivates effort to design approaches to indicating specific input tokens as being particularly influential given a test input and the corresponding prediction. In response to the motivation, some previous paper before this paper aimed to construct sentence maps over text in which the words are highlighted with the importance scores in terms of how they contribute the final prediction given a test input. And in later slides, I will also introduce the details compared to the methods proposed by this paper. However, there is a problem that they are not always suitable when model decision is driven by the complex reasoning. For example, in the example shown on the right-hand side, given two sentences denoted as P and H respectively, the task here is to infer whether the sentence P can entail sentence H, as the tokens that get the most positive and negative sentence scores are marked in cyan and red respectively, and we can see that an importance measure of each individual token might not be given us much useful insights to understand such models' prediction. And therefore, to address these shortcomings of the word silence methods, this paper investigates from another perspective of explanation by example. Instead of constructing the importance score over the input tokens, they rank the training examples by their influence on the model's predictions given a test input, and specifically, this paper adopts previous influence functions. And this figure shows a sentiment analysis example interpreted by the gradient-based silence map on the left and compared to the influence functions on the right. And note that this example is classified incorrectly by the model. And the positive silence tokens and the highly influential example with the positive influence score may suggest that why the model makes such wrong decision. And the tokens and examples with negative silence score or the negative influence scores may decrease the model's confidence in making such decision. And next, I will first explain more details about the gradient-based silence map method. In NLP, typically a BERT model takes a sequence of words as their input and processes it through multiple layers to capture the context from both directions, and then output a contextualized representation of each word in the sequence, which is useful for various NLP tasks like the classification. And to use it for the classification, we typically add a classifier layer on the top of BERT's output for the CLS token, and then fatten the model on the labeled data to predict the target class. And because we are interested in why the model made a particular prediction, therefore the loss is defined with respect to the prediction that model actually made rather than the ground truth. And for each token Ti, a silence score is defined as the sensitivity of the loss to the change in the input embedding of this token Ti, which is the ET shown in this equation, and the final silence score of each token T would be the L1 normalized across all the tokens in this given test input sentence. And in this paper, they do not take the absolute value of the silence score, as the direction can encode whether a token is positively influenced for a prediction which is providing the support to the prediction, or negatively influence the prediction which can highlight the counter evidence of this prediction. And in this slide, we will dive into their proposed approach with the influence function and its explanation by training example. And basically, their calculation of influence score for the training sample is exactly following the original influence function paper shown at the bottom. And here I will skip the details about these equations, as Professor Ma already gave us very detailed introduction during the first meeting. And note that, same as the last slide, the loss is defined with respect to the prediction rather than the ground truth. And intuitively, a positive influence score for a training example means when we remove this example from the training set, we would expect a drop in the model's confidence when making the prediction. And a negative influence score means if we remove this training example, it would increase the model's performance, the confidence in this prediction. And overall, their experiments' goal is to analyze and compare these two interpretation approaches on two kinds of tasks. One is the relatively shallow and lexical-driven task, and another one is more complex and reasoning-driven ones. And for the relatively shallow and lexical-driven task, they choose a task of sentiment analysis. Specifically, they adopt the Stanford Sentiment Tree Bank SST2 dataset, and after training on the training set to evaluate the interpretation of prediction, they further sample 50 examples from the development set from the same dataset, for which they extract the explanation for models' predictions. And for a more complex and reasoning-driven task, they choose a task of natural language inference (NLI) This is about to predict whether a promised sentence can entail another hypothesized sentence, and they train the model on MNLI dataset and evaluate the interpretation with another diagnostic subset of 30 examples from the Hans dataset, which shares the similar structures with the MLI and with the annotation of some existing data artifacts. And here are two research questions for their experiments. The first question is influence function approximation reliable when used for the deep model in NLP? And the second question is, are these gradient-based sentence maps and the influence function-based maps compatible? And to answer the first question, is influence function approximation reliable when used for the deep model in NLP? They designed an experiment by test to remove 10% of the most positively influential samples, 10% of most negatively influential, and 10% of the least influential with influence scores near to 0, and another 10% random training examples. And they will analyze how these removals in the retraining would affect the confidence of model's prediction. And from the results, they observe that if we remove the most positively influential samples from the training set, it will be a significant drop for the model's confidence for the prediction. And if we remove most negatively influential samples, models will be slightly more confident during the prediction. And if we remove the least influential samples, which with the influence scores near to 0, for the sentiment analysis task, it is similar to remove a random 10% of the training examples. And the key conclusion here is the influence functions behaves reasonably and reliably for the BERT model in both sentiment analysis task and the NLI task. And to answer the second research question, are the gradient-based sentence maps and the influential examples compatible? They designed two experiments. The first one is to answer whether a token with high sentence also more frequent in the training examples with the high influence scores. And for each test sample, they first identify the tokens with the highest, lowest, and medium sentence scores. And secondly, they find the influential training samples that contain these tokens. And thirdly, they filter these examples by the test prediction label for direct influence. And the last step is to calculate the average influence scores for these filtered samples. And the key findings here is, for the sentiment analysis task, we found training examples with most positively silent score tokens will generally have a higher influence. But for NLI task, we do not see this trend. And note that in these two figures, the positive, most negative, and medium are the silence level. And they designed the second experiment to answer whether influential results would change significantly when a silent token is removed from the input. And removing a token with the most positively silent score, we expect model will be less confident about its current prediction. And similarly, they found for the sentiment analysis task, when removed the tokens with most positive silent scores in the top influential training examples, there will be a largest decrease for the model's confidence. However, it's not the same for the NY task, that it even increases the model's confidence when remove the silence token with the positive silence scores. So the key conclusion is, for the NY task, the two approaches do not agree with each other and could potentially tell very different stories. So from this example shown at the beginning of this paper, we can actually find that the importance of each individual token might not give us much useful insights to understand model's decision, which is because the decision for the NY task, which is reasoning driven, is often made through an interaction between multiple words or spans. And through influence functions also do not explicitly tell the latent interaction between words or spans, but it can test whether the model is relying on some hypothesized artifacts in the post-hoc way by looking at the patterns in the influential training examples. And although the most influential examples, both supporting and opposing shown on the right-hand side, are similarly far from the test input, but these all exhibit lexical overlap between the premise and the hypothesized sentence. Some of the influential training examples, for example, the first supporting example and the second opposing example, capture a reverse ordering of the spans in the premise and the hypothesis, which also shown in the test input. And next, let's move to the second paper that made some improvement based on the first paper. So in the last paper, there's an issue that it requires to manually investigate the pattern of the artifact, for example, the lexical overlap from the training sample. However, to aid the artifact detection, it may be preferable that we can automatically highlight the responsible tokens in the influential training samples. And to solve this paper proposes a hybrid approach that combines the feature attribution, for example, the silence map, with the instance level attribution to identify the token level artifacts in the influential training samples to reflect some patterns of the artifacts. In their method, the first step is also the same as the last paper that given a test sample, they identify the influential training samples with the influential functions. But additionally, their step 2 is just use the previous word silence map methods and apply them on the influential training samples instead of the test inputs, and which may be helpful for users to identify the abstract artifacts in the training samples from the step 1. And in addition to analyze each influential training sample separately, we can also like to do an overall token level influential analysis from the all influential training samples. A straightforward way is to do the token aggregation. Specifically, this paper sought all the tokens by frequency that appeared in the top k most influential samples. This may be helpful to find the tokens that appear disproportionately in the influential training samples. For toxic detection sample, this might reveal that the punctuation marks such as the exclamation mark tend to occur more frequently in the influential examples, which may directly reflect this artifact behavior. And I will then introduce their experiments. They mainly conduct the case studies on various classification tasks such as the MNLI, MDB sentiment classification, and so on. And they also do the influential analysis for the BERT model. And for the instance level attribution methods, they test the RF and the EUC. Here the EUC is to use the Euclidean distance to measure how close two sentences are in the embedded space. And they show that their method can find some existing known artifacts and some new unknown artifacts in this 4 datasets. And here the notation FA and IA means the word silence methods and the influential function for the instance level methods that is the last paper that we introduced earlier. And from these examples, we can see that their method combine some strings of the FA and IA methods. And next, I will introduce the third paper, which is a more recent paper in this year that focuses more on how these artifacts influence a model's behavior during the fine-tuning process. And basically, when we're talking about the model training, we can think of it as happening in 2 main steps. The first step is the model learns what we call as the influence function, and these are essentially the patterns or the rules that the model pick up from the data during the training. And once these influence functions are learned, the model can then use them directly to tackle some new problems or make some predictions for other new data. And this two-step process helps the model generalize from the training data to new and unseen situations. And from a dataset perspective, the empirical influence function EIF helps us to see how fine-tuning a model is influenced by a single training sample. And by adjusting the model and observing the impact of one data point, we can better understand how individual inputs affect the model's predictions. This is essentially useful for the fine-tuning and improve model's performance on very specific tasks. But however, it remains unclear that during the procedure of fine-tuning, how good these systems are at applying existing data to the new domains and how much they reflect the properties that we would like a learning system to have. And ideally, the authors highlight as for the NLP model, a good influence function that learned by models through the fine-tuning should have these properties. And next, I will explain how they test these properties to understand what model can learn from the fine-tuning. And I recommend that the audience can pause here to see each of the details of these properties. And there is a problem when applying the influence functions on large language models. The previous works have shown that influence functions that are computed from the gradients and the Hessian of the model may grow fragile and for the sufficiently deep models. And furthermore, these influence functions can have counterintuitive, even paradoxical interpretations, and therefore, it's hard to explain if the unexpected behavior is a consequence of the wrong influence function or of the learning paradigm itself. Therefore, this paper adopts another alternative approach that compares the model's output difference before and after fine-tuning instead of using influence function to approximate the change of model's internal state. And more detailedly, they start with a model trained on most knowledge except for a specific part that they want to test, and by first measure how well the model performs without this new information, and then fine-tuning it on the new information, and they can see the difference in the performance. And this difference, aka the results of the EIF measures, shows that the impact of the new information, whether it helps or hurts the model's ability to perform on other tasks. And note that the EIF here measures the change in model's loss after learning from a specific dataset, indicating the impact of the data on the model's performance. And following the specific procedures introduced in the last slide, they further conduct experiments on a recent LLM called Phase 3. And because LLMs nowadays are commonly trained on a very broad and universal text corpora, it is very unlikely to find a new knowledge domain as a new fine-tuning dataset for the testing. So instead, they artificially construct a novel domain by producing structured facts from synthetically generated entity names. Specifically, they first create some new phonetically reasonable entity names, like this word, by combining some syllables. And then they construct the templates to study the properties shown in the beginning slide. And for example, to study the directivity of the ontology, they construct the simple template such as A is a B, where the A and B are filled with the newly created words. And the first key finding is there is no sense of correct transitive behavior. For example, after training on the combination of a in B and a B in C, the model is not more likely to produce higher probability for A in C than the A not in C. And furthermore, they also tried a context learning way that provides samples from the fine-tuning dataset as the in-context demonstration, during the inference and within the prompt, rather than in the fine-tuning model with these samples. And surprisingly, they found that such e-context learning way can improve the model's ontology reasoning. And in this figure, we can show that compared to the original cell A and B for the fine-tuning, replacing the fine-tuning with the new e-context learning can make the A prime much darker than the B prime cell. Here, the more darker means that it's more influential, which is what we expected for correct ontological reasoning. And the second key finding is there is no evidence of the model that should carry on the causality through chain statements. For example, we expect for the model's inference with the A to Z trained on the direction chain from A to B, B to C, C to D, D to Z should be similarly influential as trained directly on the A to Z. However, we can observe a much lighter color of the cell B compared to the cell A, which shows that the longer tree is less influential for the cell A to Z. And similarly, the e-context learning still performs better. Like we can see that the color of the influence for the cell A prime and B prime is much similar. And the key conclusion here is that the LMs, although LMs use influence function to define how fine-tuning data impact the performance, whereas the context learning processing is better to capture the desired influence function properties. And last but not the least, I will briefly introduce the last paper to give you some key insights for the specific challenge known as the cancellation effect by using the last layer of the large model for the influence analysis. So as introduced earlier, given the immense size and the complexity of these models, it's very computationally infeasible to analyze all their parameters for such large model, and therefore a very common practice is to only study on the last layer weights. So the question is, why last layer could be feasible in terms of NLP, and a lot of previous NLP works show that for the NLP models, it processes the language hierarchically, with early layers handling the basic elements just like the syntax, and for the deeper layers, it will build more abstract and context-aware representation. As the final layer focuses on the features more critical to the specific task and ensures the precise and relevant output for a given downstream task. However, this approach has its limitation, that specifically the weights in the last layer tend to equal so-called shared logic, which can lead to a cancellation effect when different examples show contradictory influence on these weights. And this cancellation effect reduces the discriminative power of the influence score, making it harder to accurately trace the impact of individual training examples on the model's decisions. Let's first dive into the concept of the shared logic in the last layer. Basically, in the last layer, the activation patterns often represent the features that are common across various different examples. And the last layer uses these shared features to generate the prediction. But this also means that the gradients for different examples can be very similar. So as a result, it becomes challenging to trace the specific influence of the individual examples on the model's output. For example, for these two sentences, the first is the cat sat on the mat, and the second is the dog sat on the mat. The last layer might produce very similar activation pattern with gradients that differ less than 0.05. Then what is the cancellation effect in terms of the data influence? When opposing data influence are present, they can effectively cancel each other's output, leading to a less accurate influence score. For instance, if two examples show strong but opposite influence, say like one with the positive 0.8 and another with the negative 0.7, and their combined effect on a prediction might be minimal, in this case just positive 0.1. And this is particularly problematic in the last layer of the model, where the shared logic is prevalent, making this layer more sensitive to such cancellation, as there will be more similar pairs with such shared features. And in contrast, that the early layers of the model are less affected by this issue, as they do not rely as heavily on the shared features as the last year. And to mitigate such cancellation effect, this paper also proposed a way called the track-in way. And they select the track-in as the influence function as it's computationally feasible compared to other influence function methods, because it directly uses the graded information at different checkpoints during the training process, avoiding the need to compute and invert the Hessian matrix. And as explained in the last slide, they found that the early layers, so-called word embedded layers, has less cancellation effect. And these layers can also transform the discrete words input into the continuous vector representation that captures the semantic meaning. This is because these vectors are designed so that the words with a similar meaning and the context appear close to each other in this high-dimensional space. So we can call them as the word embedded layers. And the key result of these experiments show that their method can outperform other versions of the influence methods that calculate with the last layer of the model or the language classification task in terms of the rate of the cancellation effect. Okay, here are some key takeaways of my today's presentation. In the first paper that we introduced how to use the influence function to interpret NLP models at an instance level in the training set compared to using the feature attribution such as the word sentence maps at the token level of the test input. And the second paper furthermore show that from the influential training samples, we can apply the feature attribution on these training inputs to highlight some key patterns that can reflect by the words. And the third paper shows us fine-tuning may not allow LMs to study the correct reasoning, but maybe the context learning can be helpful. And the last paper shows us that the influential analysis of the last layer may be less accurate compared to using the early layers due to the heavily shared logic and the cancellation effect from the last year. Okay, that's it for my today's presentation, and thank you for watching.